The call to close the gates and return to the current implies a need for proactive measures to protect one's spiritual well-being and to engage with one's faith more deeply. Additionally, the encouragement to share personal struggles with trusted individuals underscores the importance of community and vulnerability. It serves as a reminder that no one should face their burdens alone, and that opening up can create pathways for healing and understanding. This is a poignant invitation to foster connection, encourage dialogue about faith and struggles, and support one another as we navigate the complexities of our spiritual journeys. Do you think you understand the age of the universe? 13.8 billion years. That's what everyone says. But here's the uncomfortable truth. Most people accept that number without ever wondering how we actually figured it out. Let me show you. Richard Feynman had a principle. He said, "The first principle is that you must not fool yourself, and you are the easiest person to fool." So when you hear 13.8 billion years, it sounds so precise, so definitive. More or less 20 million years margin of error. Impressive, right? But stop for a moment. Think about what that really means. Feynman hated what he called cargo cult science. Here's what that means. During World War II, American soldiers built air bases on Pacific islands. The locals saw planes land, bringing food and supplies. When the soldiers left, the locals built fake runways out of wood and bamboo, thinking the planes would come back. They copied the shape, but they missed the whole point. Feynman said a lot of people do science the same way. They memorize the numbers. They memorize the formulas, but they don't understand where they come from. So let's apply Feynman's filter here. 13.8 billion years. Where does that number come from? Have you ever asked? Most people don't. They just accept it. And that's exactly the problem Feynman identified. The difference between knowing and actually understanding. Pause here. What do you actually mean when you say, "I know the age of the universe"? Did you measure it? Did you run the calculations yourself? Or did you read it somewhere and memorize it? If it's the last one, you don't know it. You're just repeating something. And repeating without understanding is exactly what Feynman warned against. Here's the real problem. Nobody was there 13 billion years ago with a timer. We didn't film the universe being born. So what are we actually measuring? Not time, not directly. That's impossible on a cosmic scale. Think about it like this. You show up at a crime scene and find a body. You didn't witness the murder, so how do you figure out when it happened? You check the body temperature. You look at rigor mortis. You examine decomposition, then you piece it together. Cosmology works exactly the same way. We measure things we can see right now, and then we work backward through a chain of logic. Feynman always said, be clear about what's a fact and what's an assumption. Here's a good example. Pluto's mass. Before 1978, we thought Pluto was about 1% of Earth's mass. That was precise. Published everywhere, taught in classrooms. Then we discovered Charon, Pluto's moon, and did new calculations. Pluto's actual mass? 0.2%, 5 times lighter than we thought. The number looked solid, but it was wrong, because our assumptions about what we were looking at were wrong. Same thing with the speed of light. Back in the 17th century, Olaus Rømer first tried to measure it. He calculated 220,000 kilometers per second. Seemed solid for the time. Today we know it's 299,792.458 kilometers per second. He was way off. Why? His measurements were based on watching Jupiter and its moons, and he made assumptions about distances that turned out to be wrong. Precision doesn't guarantee certainty. That's Feynman's lesson. You can have a number with many decimal places and still be fundamentally wrong if your assumptions are incorrect. And when it comes to the age of the universe, we have a lot of assumptions. A lot. But here's what bothers you. We're not measuring something we can hold, see with our own eyes, or test in a lab. We're measuring something that supposedly happened billions of years before humans existed. Before Earth existed. Before the sun existed. So if we can't measure it directly, what are we really doing? That's Feynman's question. And it's what you should be asking. If you accept 13 billion, 800 million years without understanding the logic behind it, you're exactly what Feynman warned about. You're building bamboo runways and waiting for planes to land. So, if we can't directly measure 13 billion years, what are we really measuring? Let's reveal the whole chain. First, let's talk about light. Not the light you turn on at home. The light that travels across the universe. When you look at a star in the night sky, you're not seeing the star as it is now. You're seeing how it was when that light left it. Some stars you see may already be dead. The light is still traveling. This is basic, but crucial. Now comes the interesting part. In the 1920s, an astronomer named Edwin Hubble was studying distant galaxies. He noticed something strange. The light from those galaxies was stretched, shifted toward the red. Redshift. Let's understand what that means. Ever hear an ambulance pass by? When it comes toward you, the siren sounds high. When it moves away, it drops to a lower pitch. That's the Doppler effect. The sound frequency changes based on whether the source is coming or going. Light does the same thing. When a galaxy is moving away from you, the light it emits is stretched. The light waves become longer. Longer light means redder in the visible spectrum. That's why we call it redshift. The faster the galaxy is receding, the greater the redshift. Hubble measured this in galaxy after galaxy, and he noticed something remarkable. The farther away a galaxy was, the more redshifted it looked. The farther, the faster it's moving away from us. That's Hubble's law. Simple pattern. Distance is proportional to recession speed. Think about what that means. All galaxies are moving away from each other. The universe itself is expanding. No center point. It's not like everything is rushing away from one spot. It's that space itself is stretching. Picture dots on an inflating balloon. As it blows up, the dots spread apart. But none of them is the center. So we have this observation. The universe is expanding. But how does that tell us how old it is? Here's the logic. If it's expanding now, it must have been smaller before. Much smaller. Rewind the tape far enough and everything gets crammed into one dense, incredibly hot point. That's the Big Bang. So when did that happen? If we know how fast it's expanding now, we can work backward. How long would it take to go from a single point to where we are today? It's like two cars driving away from each other at 100 kilometers per hour. If they're now 200 kilometers apart, they've been driving for 2 hours. The problem is the expansion rate wasn't always the same. It changes over time. In the early billions of years, gravity was pumping the brakes. Then dark energy kicked in and started accelerating everything. So the math gets complicated. You need to model how the expansion rate shifted over time. And that depends on what the universe is actually made of. How much regular matter, how much dark matter, how much dark energy. But there's another piece of evidence. Maybe the most important one. The cosmic microwave background radiation. The CMB, discovered in 1964 by Arno Penzias and Robert Wilson. And it was totally accidental. They were using a radio antenna trying to get rid of static for satellite experiments. But there was this constant hiss. From every direction. No matter where they pointed the antenna. Always there. They cleaned it. Got rid of pigeon nests. Nothing helped. The hiss kept coming. Temperature, 2.725 Kelvin. Cold, just a few degrees above absolute zero. What did they unknowingly discover? The echo of the universe's birth. What is it? It's the echo of the Big Bang. When the universe was very young, about 380,000 years after the Big Bang, it was extremely hot and dense. So hot that electrons and protons couldn't combine to form atoms. It was a soup of charged particles, and light couldn't travel freely. It was constantly absorbed and re-emitted. The universe was opaque. But as the universe expanded and cooled down, electrons and protons finally came together to form neutral atoms. At that point, light could move freely for the first time. That light is still traveling through space. That's what we detect as the cosmic microwave background. Think about that. When you look at the CMB, you're seeing the universe when it was just 380,000 years old. You're watching the past, not a picture of it. The actual past arriving now. The temperature of that radiation tells us something key. It's 2.725 Kelvin now. But when it was emitted, it was about 3,000 Kelvin. So it cooled by a factor of about 1,100. That cooling is tied directly to how much the universe has expanded. More expansion means more cooling. So we measure the CMB temperature, calculate how much the universe has stretched since then, combine that with galaxy redshift data, plug it into models based on Einstein's general relativity, and we get a number. 13,800,000,000 years. give or take 20 million years. Sounds pretty solid, right? Two different pieces of evidence. Solid math. But Feynman would point out something. Every step in that chain is working backward from something, not direct observation. It's all interpretation based on models. You see redshift. You assume it means motion. You assume light behaves the same everywhere in the universe. You assume the Doppler effect applies on cosmic scales. You see the CMB. You decide it's the echo from the Big Bang. You assume thermodynamics worked the same way 380,000 years after the universe started. Each step works great if the assumptions are right. But they're still assumptions. Feynman's question, can you actually test them? Or are you just accepting them because the model needs them to work? So the chain of reasoning is elegant, clever, but it rests on interpretation. And this is where you see the difference between a number looking precise and actually being certain it's right. 13.8 is precise. But are we really sure it's correct? Wait a bit. Because this question has an answer that will make you more uncomfortable. And it's the answer Feynman would give. Let's talk about the hidden assumptions. The major ones. The ones buried in technical papers, not discussed much in public. When you calculate the age of the universe, you're betting on three fundamental ideas, and you can't prove any of them. Here's where it gets interesting, and where most people never go. First assumption, the laws of physics haven't changed. When we look at the light from a galaxy 10 billion light-years away, we're seeing light that was emitted 10 billion years ago. And we assume that the speed of light was the same, that the electron's charge was the same, that the gravitational constant was the same. But how do we know? Can you design an experiment to test if the gravitational constant was the same billions of years ago? You can't. You weren't there. You can't build a time machine. That's Feynman's question. How do you test if physics was the same billions of years ago? You can't travel back. You can't run experiments in the past. All you can do is look at ancient light and check if it acts like the physics we know today. And it does, as far as we can tell. But that's not proof. That's just consistency. Here's an analogy. Imagine you're measuring a race, but your ruler is made of rubber. As you measure, the ruler is stretching. You can get numbers, sure, but what do those numbers really mean? But imagine you don't even know how much the rubber stretched. You just guess. You create a math model of how much it stretched and hope you're right. That's what we're doing. We're measuring the universe with light that traveled for billions of years through space that was expanding the whole time. We're using a ruler that was changing, and we're assuming we know exactly how it changed. Second assumption, the universe is homogeneous and isotropic. That means the universe looks the same no matter which direction you look and where you are. Whether you're here or 10 billion light-years away, you see roughly the same arrangement of galaxies. Same average properties. Think about that. It's like saying if you find an ant in Sao Paulo, all ants on Earth are basically identical. The ones in Africa, the Arctic, the rainforest, all the same. Would you buy that? Probably not. But we do that for the universe. That assumption is called the cosmological principle. It's at the foundation of all expansion models. If the universe isn't uniform, if there are huge regions we can't see, then our math falls apart. We calculate age from what we observe. But we only see a small part. The observable universe is just the zone where light has had time to reach us. Beyond that, unknown. Unknowable. So we assume it's basically the same. But really think about it. Is it reasonable to assume an entire universe may be infinite is uniform, based on what we see from one spot? It's like being in a dark room with a flashlight and deciding the whole building looks like that small circle of light. Third assumption, and perhaps the most problematic, dark energy. Or more specifically, the dark energy model we use. In the 1990s, astronomers discovered that the universe's expansion is not slowing down. It's accelerating. Stop and think about this. You throw a ball up. Gravity pulls it down. It slows. Makes sense. Now imagine the ball speeds up instead. Faster and faster. No reason why. That was a shock. Gravity should be holding everything back, slowing expansion. But it's not. Something is pushing the universe to expand faster. We call it dark energy. But honestly, we have no idea what it is. It's just a label for what we don't understand. And this is the embarrassing part. About 68% of the universe is made of this thing we don't know. the thing making space expand faster. Think about that. 68%. More than 2/3 of the universe is made of something we don't know. And when we calculate the age of the universe, we have to include the effects of dark energy in the model. But how do we model something we don't understand? We use something called the cosmological constant, the Greek letter lambda. Einstein introduced it in 1917, later said it was his biggest blunder. Then in the 1990s we found out maybe he was right. But here's the catch. The cosmological constant assumes dark energy stays the same density over time. Is it? We don't know. Maybe dark energy density changes. Maybe it acts differently in different eras. If it does, our age calculation is wrong. So here's the issue. 13 billion. 800 million years comes from models that bet on constant physics, a uniform universe, and a specific dark energy model. Change any one of those assumptions, the number changes. And here's the uncomfortable truth Feynman always made clear. You can't directly test those assumptions. You can check if the model is logically consistent. You can check if it makes predictions that match reality. But you can't test the basic assumptions, because they're beyond what we can directly observe. It's like building a house. You can test if walls are solid, if the roof leaks, if doors close. But whether the foundation's on sand or rock, you only find out when the earthquake hits. In cosmology, that earthquake might never come. Or it comes in 100 years when we discover something that flips everything we believed. It's like measuring the temperature inside the sun. You can't shove a thermometer in there. So you build a model using nuclear physics, thermodynamics, and what you see on the surface. The model says 10 million Kelvin. Do you trust that? If you trust the model, sure. But you didn't measure it. You calculated it. Now, does that mean 13 billion, 800 million years is wrong? Not necessarily. But it does mean it's an answer based on models, not a direct measurement. And that distinction is everything. Imagine using GPS. It says you're 500 meters from your destination. Pretty precise, right? But what if the satellites are off? If the signal's delayed? If there's a glitch? The number stays precise. But it could be dead wrong. Feynman's rule, the first principle is don't fool yourself. And here's how you fool yourself. You confuse a precise-looking number with actual certainty. So where does that leave you? Should you discard the age of the universe? Throw out all of cosmology? Absolutely not. Feynman wasn't saying that science is wrong. He was saying science requires intellectual honesty. You need to know the difference between what you measured and what you assumed. 13 billion, 800 million years is the best answer we've got, based on the best evidence and models we have. But it's not the answer. It's an answer. The difference between those is huge. Real understanding of that number means, you know it comes from measuring redshift and the cosmic microwave background. You know it depends on assuming physics was always the same, that the universe is uniform, that dark energy works one specific way. You know that if any assumption is wrong, the number's wrong. Does that make you trust the number less? Maybe. But it makes you smarter about science. Real science literacy isn't memorizing numbers. It's knowing where they come from. It's knowing what they actually mean. It's knowing what they don't mean. Feynman was comfortable with not knowing. He said, I can live with doubt and uncertainty. It's more interesting to not know than to have answers that might be wrong. That's the real lesson. Uncertainty isn't weakness. It's honesty. It's the difference between doing real science and doing fake science. Think about how this applies to other areas of your life. How often do you accept numbers, statistics, claims, without asking where they came from? How often do you hear something that sounds precise and assume it must be true? 97% of scientists agree. Studies show it. Experts say so. And you just take it as fact. But have you asked, which study? How'd they do it? What assumptions did they make? How many people? How were they picked? If you don't know that stuff, you're not thinking scientifically. You're just parroting something. Feynman would tell you to be skeptical, not cynical. There's a real difference. Cynicism says, nothing's true, everyone lies. Skepticism says, show me, prove it, let me see the logic. And for the age of the universe, that chain is long and complicated. It rests on assumptions that might be right, but can't be proven. That doesn't kill the usefulness of the number. It just makes it conditional. If physics is constant, if the universe is uniform, if dark energy works like we think, then yes, 13 billion. 800 million years is our best estimate. But wait, there's more. Even if all those assumptions are right, something philosophically weird is happening. The universe's age depends on your reference frame. In general relativity, there's no universal now. Time is relative. So when we say the universe is 13 billion, 800 million years old, we mean relative to what? To an observer at rest, relative to the cosmic microwave background. But that's arbitrary. That's a choice of reference frame. Not an absolute truth. A relative one. If you were traveling near the speed of light, the time you'd measure since the Big Bang would be different. Not a little different. Possibly very different. So the universe's age isn't a fundamental property of the universe. It's relative to the observer. Think about that. What does measurement even mean when the answer depends on how fast you're moving? Feynman loved those paradoxes. He didn't see them as problems. He saw them as how reality actually works. Reality doesn't owe us simplicity, doesn't owe us easy answers. When you accept that, when you really accept the universe is weird and we don't understand it all, something shifts. You stop lying to yourself. You stop mixing up precision with being right. You stop assuming a number in a paper is gospel. You start asking the real questions. Not, what is the age of the universe? But, how do we measure it? What are we assuming? Can we test those? What if they're wrong? Those questions matter more. They show you how knowledge works, not just the bottom line. And those questions are worth more than any answer. Because answers change. Pluto's mass changed. Light speed got refined. Earth's age got updated multiple times. But asking questions, that never changes. That's the scientific method. Don't just accept numbers. Know where they come from. So here's Feynman's challenge. Next time you hear a scientific claim, a